Hi, good morning, Chemistry 352 students. First, I must say it's good to be back after doing some going on business for the university. And I must thank Raj for filling in for me with your pre-lab lecture. And Raj, from what I have spoken to you, you've done a wonderful job. But one thing I have realized, is that many of the students really are not reading the material posted on Blackboard. I've shown you guys these slides regarding experiment 4 details. I've mentioned about crystal field theory. I've shown you about the transition metal gems. Here is the crystal field theory as explained. Remember, these are all posted on Blackboard. The energetics regarding the electrostatics between the metal ion and the donor atoms. And those donor atoms are from the lowest bases. Here, about the interaction, ligand to metal. Here, what happens in the orthohedral field. Here, regarding the splitting of the d orbitals. And one thing about the 10 dq or the delta, where according to the spectrochemical series, where you're going from a weak field to a strong field and increasing in delta, and that's the frequency. Here, electronic configuration for high spin, low spin complexes. Here, high spin versus low spin. And colors and how we perceive colors. Also, what happens in black and white, absorption, reflection. And what happens in terms of electromagnetic spectrum, in terms of spectrophotometer. Here are the various colors for the iron, cobalt, is cobalt 2, nickel 2, copper 2, and zinc, which has 10 d electrons, so therefore it's going to be colorless, no d to d transitions. And here are the various colors for the complexes. So you notice all of these are all cobalt 3 complexes, so be very careful regarding the overall charges. Here are the various splittings, and one thing is that you really have to know these for Professor Bay's course as well. And here's a summary, magnetism, and remember I mentioned about magnetic measurements as well, where I must mention S is the number spin with the number of unpaired electrons divided by 2. Here the various for species, the number of the electrons, and all unpaired electrons must be, and the spin and the magnetic moments. Here is an example. Remember we went through this as well. And here this is the equation used in order to calculate the number of unpaired electrons. And also remember to utilize this equation as well. And once you've done that, you need to show two examples. One, electronic configuration being high spin or low spin. Remember, we've mentioned about you draw the magnetic susceptibility measurements. Is what you utilize in the lab. And these are just some items for the pre-lab, which I mentioned you all should have known as well. And remember, in terms of redox potentials, also hydrogen potential, redox potentials in terms of reducing ability, also the standard redox potentials. Here gets the hydrogen electrode. Remember, this was used for the lab with vanadium. These are the various colors. These are all posted. Vanadium 4 as well, 5 to 4, 4 to 3 redox potentials off of the half cells. And remember, vanadium 4 is what it looks like in terms of structure. And this is what it looks like in the lab. The vanadilyl cation is vanadium acac. You've seen a photograph courtesy of Raj. This is the infrared spectrum, and these are the structure frequencies where you have to really identify them and mark them as well. For V.10, this is the UV visible spectrum for the vanadilyl complex in solution. Well, this is amavadi, which is vanadium 4 species with a 8 coordinate species, and this is where now the big areas used to live. And again, you remember in terms of color for experiment 8, I advise you guys to read it because you all are really not reading the slides as posted in the pre-lab as well. Again, remember you have to convert from nanometers to meters and then to centimeters, and then you find the reciprocal. And one thing as Raj mentioned, 1 meter is equivalent to 100 centimeters. 1 meter is equivalent to 100 centimeters, and nano means 10 to the minus 9. And of course, angstrom means 10 to the minus 10. Colors absorbed, color observed. Limitations, remember you're asked to find out the limitations as well. The limitation for the crystal field theory. This is spectrochemical, weak field, strong field. And here, according to, you can see that cyanide splits it much greater than fluoride. These are the colors absorbed, color emitted. Again, right here as well. And that's in that slide. Now, regarding Lewis dot structures, I'm going to give you guys a little preamble about the Lewis dot structures. I'm going to give you guys the proper way of drawing the Lewis dot structures. Now, it's very important that you need to look at these YouTube videos. They are listed. And when you draw a Lewis dot structure, you must use dots to represent electrons. Use all dots, not a single bond or double bond, which of course you don't do that. You have to use the dots. That's why it's called the Lewis dot structures. Please be very careful in the future. Again, this is a single bond. It's a lone pair of electrons here on the oxygen. This is a single bond. This is a single bond, and this signifies a triple bond, and this is a double bond. And this is how you draw the Lewis dot structures. Please remember that. Okay, please, you have to show all of the dots, no dashes. Again, as you know, hydrogen has 1 dot. The group 1 elements has 1, remember, valence electron, so it shows in group 1, and group 2 has 2, group 3, group 4, group 5, group 6, group 7, and group 8. Remember it's fluorine as well, so be very careful how you draw your dots. Again, this is BeCl2, and you have to draw the structure according to how the shapes are. This is linear and not bent. This BeCl3, which is trigonal planar, you have to be very careful how you, of course, complete the octet. But in this case, this has 2, 4, 6, and in reality, this will form a data covalent bond, and the octet around the boron is really not complete. So this octet is not complete. This is for boron chemistry as well. But be very careful when you draw the structures. This is a nitrate anion using the Lewis dot structure. Please be very careful as well. This here is how carbon looks like. This is fluorine as an atom. Okay, this is CF4. Okay, and this is how you draw the Lewis structure here, not like this. I'm just showing this how this signifies that this is a single bond, but here is how you draw the Lewis dot structure. Please be very careful, and this is for fluorine as well. Now, this is ethylene diamine tetraacetic acid, and commonly known as EDTA. I will let you guys practice drawing all of the dots. And bear in mind, there's a lone pair of nitrogen here, a lone pair of nitrogen here. Don't forget that. And you can see it has 1, 2, 3, 4 carboxylic acid groups. This is a carbonyl. This is an OH group. So please note, this is a carboxylic acid here. And the reason why it's called tetraacetic acid because it has 1, 2, 3, 4 carboxylic moieties. And you can see the ethylene part. It has carbon atom 1, carbon atom 2. Remember, similar to ethylene diamine. Ethylene diamine has NH2, CH2, CH2, NH2. This is EDTA. Okay, so please note that. You can try it for pyridine. You can see pyridine here has a lone pair of nitrogen, and pyridine is aromatic. It's a heterocycle where 1 nitrogen has replaced 1 of the 6 carbons in benzene. Note that the alternating double bond, but try it. Remember, this is just a structural formula. Likewise, this is a structural formula here for EDTA. Okay, You can try it for glycine. This is what glycine is. Remember, the simple amino acids, some it's like, you know, like alanine, but this is glycine. It's as an amino acid. And you can see it's chiral as well, in a sense. Okay, so be very careful how you look at those structures, and please note that. Now, regarding the pre-labs, let's look at pre-lab questions for, this is for experiment 6 for iodine trichloride. You are supposed to download, this is for the questions E, part 4. You're supposed to download the following articles and briefly discuss the uses of iodine trichloride by using a maximum of 2 pages, no less. So this was supposed to be this is supposed to be 4 pages in length for this question. And you're not supposed to have done less than 2 pages. So you all really need to read and understand the articles. Once you have the articles, they're simple as such. You have to utilize every reference I've given to you as well. Please, if you don't do that, you're not going to be succeeding in being a good chemist as such. Now, that's experiment 6. For experiment 7 here, these are all very simple because these are really in the same textbooks and the references pertaining redox potentials. I mean, many of you guys are drawing the structure and forgetting the overall charge. Please read. Look at this. I mean, you go, the textbooks are there on reserve. You gotta be really, and many people said they didn't understand what is a Montreal protocol on substances that deplete the ozone layer. This is really where you can practically check it out online, and this is actually just doing a Google search. I'm really amazed that many of you all are not reading. And for experiment 8, this is the pre-lab. We have to draw the structures as well, you know, for water, ammonia, ethylene diamine. Please, you guys should have done a better job in that aspect. Experiment 9, pre-lab. Once again, this is where you guys should have read and also do some reading because the references are there. Many of you all didn't utilize the table, set it as I was using Microsoft Word. Scrappy, bad presentation. All of these are given, and this is experiment 9. Clearly, experiment 9, you go here. I'm going to show you. This is experiment 9. You go to experiment 9, and experiment 9, if you read it very carefully, you acquire the FTIR spectrum. More important, beneath here, this book here this is really helpful, very helpful. And I have posted on pages 288 and 289 on a textbook by Nakamoto. Is on your blackboard about BB means. You should download this, and trust me, this would have helped you guys understand the pre-lab for experiment 9. Simple. What would happen when you use red and blue litmus? Obviously, you have to really talk about the color changes, right? Blue litmus will turn red on an acidic gas. Red litmus will turn blue on an alkaline gas. And the only alkaline gas there is ammonia. When you carry an experiment, when you have to find the purity, you have to do a titration. And clearly, you all are not really reading. Here, you have to look at experiment expected structure frequencies by just looking at the Nakamoto and the reference I've given you guys for experiment 9 as well. In terms of experiment 9 this reference number 1 has a lot. The Brawl, which is a PDF file, is very informative. You can download this online in the library. For example, I'm not going to get it now because I'm not at ODU. I'm not ODU. But once you're ODU, you can practically get this for free. You don't have to pay for it as such. It's a very beautiful. You can see here, learn a lot about that. And in conclusion, please do well. And please read. And come and see me if you have any problems. Good morning. Have a beautiful Saturday.